Obviously not really shown accurately in the graph, but that's all that taking the derivative is saying. Now, all this talk has been about slope vectors. How do you connect this to tangent lines? As you know, the slope vector of a curve is describing the slope of the tangent line at that point in the curve. But this, just like in like y equals mx plus b, the slope is only half the battle. We still have to make sure it touches the point that you want it to touch. And that point is going to be wherever your curve is at t equals 2 for this example. So what you'll end up doing is your tangent line equation is going to be your x component of the what's it called? X, oh god, what? X component of the tangent line of the of the slope vector of the tangent line. My bad. Oh my god, brain fart. I just got distracted. Actually, before I do that, let me go into one more part. Y equals mx plus b. That's what... Oh, how did I just delete all that? You've been using y equals mx plus b for a really long time. But if it was just... if it was just m only describes one portion of the entire line. The rise over 1 of one specific portion. You add the x in to extend that portion outwards to make a line. But this line, y equals mx, touches the origin. That's not necessarily true. The line might touch this point here, which is where the b comes in. So if you were to describe this with slope vectors, you would have a vector stemming from the origin that does not touch the plus b. So in order to make it touch the plus b, you multiply it by t to make it extend, first of all, to make it one line, and then you add some constant to make that line touch b. We're going to have to do a very, very similar process to get a similar result. Except now we have a parametric equation. X, Y, Z. First step, your slopes. This is your x component of the slope of the tangent line. You multiply by t to extend it to one whole line. And then plus... I'll use b for continuity. B1. Same process, but now we don't know what the second constant is. And all these are saying, this should be plus. All these are saying is that it doesn't necessarily go through the origin. It might touch another point. And for a curve, it's most likely going to touch another point because you know that it has to touch the curve. So that's all the B1s, B2s, and B3s are saying. So that is pretty much the equation. I'm going to do an example to go over in application. But I think the concepts here and the idea of slope vectors and how they work and how they transform into the tangent lines is important. So I'm gonna be doing the rest of this, the example problem that I'm just gonna make up on the spot. And I'm not going to justify anything except for the last step where you find B1, B2, B3. Everything else I've already talked about in this video, so if you need the justification, just scroll back a little and it'll be there, and text me if you need anything else. But I'm going to be trying to go through this because I think my sister wants to watch the newest Percy Jackson episode, and I want to do that too, so I'm going to go do that. Let's make an equation. t cubed plus t plus 5, y equals 2t squared plus 2, and z equals t squared plus t.